Hello, ladies and gentlemen. Welcome to your video notes regarding logarithmic functions. Please see the agenda so you know what your homework assignment is as you are taking notes to the current video. First, we are going to start reviewing by looking at what inverses are. So if you remember inverses from first semester, inverses are when two functions are essentially the exact opposites of one another. We solve them by one of two methods. We either put composition of functions, which is the first notation that you see here, by putting one of the functions inside of the other to obtain x as your final answer. If you did that for both functions and both of them equaled x, then you had two functions that were inverses of one another. Or our other method was by switching the x's and the y's. So as we're going through the first function, I'm going to use method number 2. In this case, we're going to switch the x's and the y's in both of these spots. And our goal is to now solve for our y's. Well, the first thing we need to do is get these y's, hopefully, all by themselves. In that case, we have an xy plus a 3x that's equal to a y minus 5. Our goal, again, is to get those y's all by itself. So I'll subtract y over to the other side, and I'll move that 3x over to the right side and make it negative. Now, we can factor out that y or have a little GCF in this case. And on the opposite side, I have a negative 3x minus 5. Our y is almost entirely by itself. And as we divide by an x minus 1, divide by an x minus 1, we get our y is equal to a negative 3x minus 5 all over an x minus 1. And our goal now is to check to see if that is the same as our other equation. And you may look at that and you may say, well, it's not. The signs are all different. But that actually makes these two functions inverses of one another because the 3x is the opposite sign, the 5 is the opposite sign, the x is the opposite sign, and so is the 1. But now we do the exact same thing for the other function. So the method is going to be very similar. We have a 3y plus 5 all over a 1 minus y. Our goal is to get rid of that denominator the same way that we did on the last time. So that means we have, after we actually distribute that, x minus xy is equal to 3y plus a 5. Our goal is again to get the y by itself. So I'm actually going to add the xy over to the other side, subtract the 5 over. So now I have a 3y plus xy. As I get to this spot, good news, I can factor out a y. I'm left with a 3 plus x. I get the y by itself by dividing 3 plus x to both sides, and voila, this is the exact same equation as the other functions. So we proved that these two are inverses of one another. Okay? You may say, well, why in the world are we reviewing inverses? It's because we're going to look at the inverse of an exponential function. So everything we've been doing so far in the progress on Friday is all about exponential functions. An inverse of an exponential function is known as a log. So if you notice the equation that I have up on the board, it's a 4 raised to the x power that's equal to 7. If I asked you to solve this for x, you might be kind of stuck. It's not 4 to the first, it's not 4 to the second, because that's already 16. You're really stuck in the middle somewhere. You know it's 1 point something, something, something. The only thing we could do is use our graphing calculators until we know the log form. So in this case, on the left side, you will notice what the exponential form of any basic function is. Y equals a b to the x, where b is the base. We have a very similar form with our logs, but now we have a log, and then we have a base b, and then the y is directly next to it. It's equal to the x. So you may wonder, well, how do you read this? You read this as the log base b of y is equal to x. So again, log base b of y is equal to x. And you'll know that certain things here kind of look familiar between these two. There's y's in both. There's a b in both. There's an x in both as well. So on the left-hand side, I have a log equation. I have a log base 2 of 16 is equal to 4. Now notice the colors that I have here. The 2 is the base on the left-hand side, and what do you know on the right-hand side? Where is the 2? It's still your base. As you're looking at the red part now, the of y, or the of 16, is actually now moved into the equal sign. And as we finish it out, in terms of the log, the 4 that we had after the equal sign is actually now the new exponent that you have as you are rewriting. So this is the exact same process as what we started today with when we were solving and switching the x's and the y's. This is essentially switching the x's and the y's, but in this case, it's exponential and log form. So if we were to go the opposite way and we were given an exponential to start, 3 raised to the 4th power is equal to 81. If we switch that into the log form, we could then say that it's log base 3, the base is still the same, of 81, because that's what the equal sign was, or now it's actually equal to 4. So let's try that then. Okay. We have a log function that we're given, and we want to change it to the exponential form. So our goal is with the bases. We know our 8 is the base, so that still has to be the base of our new exponential equation. And the part that is after the equal sign now is the part that we raise the base to. So a log base 8 of a half is equal to a negative 1/3. Well, we changed that so far to an 8 raised to the negative 1/3. If we actually would check our calculators to find what that's equal to, we would find that we would get a 1/2 for this particular function as well. And it's always a good idea to check yourself as you're changing from exponential to log form. Now we look at the second example. Now we have a log base 1/4 of 64 is equal to a negative 3. So again, look for that base. The base is a fraction. That's all right. We have our 1/4. If we're going to end up with a 64, that's hopefully a big tell for you guys that we have to raise this fraction to a negative exponent to get rid of the fraction. So we have the 1/4 raised to the negative 3rd now is equal to 64. We changed the order of these two. So what we're going to do now is we're going to go the opposite way. And we're going to change the exponential that's given to us into a log form. So our answer should now have a log in it. Well, as we're doing that, we always still want to look for the base. What is your base? In this first example, it's a y. So we have a log base y, and then what we're going to put next to the y, the base, or what is the of part? You notice that in the examples we did on the top of this page, whatever was originally after the equal sign goes in the exponent. So we have a log base y of a 3x would be equal to a negative z. We can rewrite these even when there's not numbers involved and it's all variables. Last but not least, as we're trying to finish the second example on this particular section, again, find out what the base is. We know we have a log base 1/9, and then it's going to be of y plus 1 is equal to whatever the exponent actually was, and it's a negative 2x. It would be a really good idea to make sure you put the of part in parentheses, just so we don't confuse either one of these two pieces. Now, we have a few different things that come up, and I'm not going to say I'm going to try to trick you on these things, but if you're looking at a common log, notice how there is no base. There's no number to it. No number means that the base is actually 10. So there are going to be some times where there may not be a number in the base for one of your logs, and if you see that, you know it's going to be the number 10. Now we have this other thing where a natural log. Okay? This is still an inverse function to an exponential function. But the key with this is when we use natural log, notice what the base actually is here. A natural log means it's going to have a base of e. So we get this 2.7 blah, blah, blah number as we continue all the way through. So it's going to be really important that we understand what the difference is when we're dealing with a common log versus a natural log. All right, now we have the final page of notes for today to finish your video, because what we're trying to do is we're trying to write these actual final answers. Okay, so we want to find the exact value. So we have a log base 5 of 25 is equal to what? So our goal for rewriting this, we know we're trying to find the x essentially here. We have a 5 raised to the x power is equal to 25. Well, we know that the only number that makes that equation work would be 2. So in the first example, x would be equal to 2. Second example, we have a log, and then there is no base, and then 1,000 again is equal to our x. So the key here, we got to figure out what is the base. We know that if there is no base, it's a base of 10. So if we rewrite this, change it into our exponentials, 10 raised to the x is equal to 1,000, and this would make our x be equal to a regular row 3. 4 more examples here. You notice they don't take long. It's really important that we're rewriting these so we know what the actual answer is going to be. Okay? So with the next one, we have log base 2 of 1/8 is equal to what? So again, notice how in this case, the x is again after the equal sign. So when we rewrite this, we can rewrite this as a 2 raised to the x is equal to a 1/8. So you have a key here. What power does that have to be? Since you're creating a fraction, that means you're going to have a negative exponent in some way, shape, or form. So your thought process is saying 2 raised to what is an 8? Well, since that answer is a 3, we know that our answer for a 1/8 has to be negative 3. The next one, it's a little tricky here, because it may help you to put this number into your calculator to try to actually find the exact value. So in this case, again, we know we have an equals x at the end. We have a 5 raised to the x power is equal to the 4th root of 125. So when you do that, and as you're putting in that 4th root of 125, oh boy, don't think too hard about this. 5 to what power is equal to 125? Hopefully you can figure that out pretty quick, because you know the answer would be 3. Since you have a 4th root on here, your x would just have to be equal to a 3/4. And that's it. The last 2 examples you'll notice deal in some way, shape, or form with an e. So for the next one, we have a natural log of x is equal to 4. We know that the base is an e. So what that tells us is we have an e raised to the 4th power is equal to x. In this case, you have 2 options. You can leave your answer as an e to the 4th, or you can actually find out what the decimal is. Since our goal is to find out what x is, I'm going to just leave my answer as e to the 4th. We could find a decimal, but you know what? Keep on going and not stopping. Okay. Last, but most certainly not least here, as we're going through, we have a natural log, so we know the base is an e, and then of an e to the 3rd power is equal to x. So our base is raised after the equal sign, and then we actually have it equal to the other part. So if we're trying to make these 2 equations equal to one another, there's only one number that can make them actually equal, and that is a 3. If we put a 3 in place of x, then we would have the exact same number on the left and the right side. Your goal now is to see how much of the homework assignment you can get done. Page 447, numbers 1 through 53, every other odd. Please make sure you're checking your answers in the back of the book, and the answer key is located on the front table in case you need that as well.